Welcome everybody to this week's IFML talk. Purna is our speaker and she'll be talking about Ojaz algorithm and estimating the error. This is joint work with Rachel Ward, whom we all know, and also Robert Lund, who was a postdoc here with Purna and is currently at Michigan and on his way to math department in WashU in St. Louis.
For those who don't know Purna, she's a professor in SDS.
Yeah, I'm sorry.
Here at UT.
Yes, I thought everybody knows Purna. Purna, thanks a lot. We're looking forward to the talk. I'll turn it over to you.
Oh yeah, thanks for the really nice introduction. Let me share my screen. Okay, can you all see my screen fine? All right, so I'm going to talk about bootstrapping the error of Ojaz algorithm. And like Konstantin said, gave a very nice introduction. This is joint work with Robert and Rachel, and a shout out to them.
We see your screen, but it's not full screen.
That's the one I want. It's good now, right? You can all see it? Yes? Awesome, perfect, thank you. Right, so yeah, this is the picture of the collaborators. So here is kind of like an outline of what I'll talk about. And I felt like maybe you all already know what Bootstrap is, but I thought I'll just have like a few slides about Bootstrap and what it does. Typically, I just take it for granted for statistics audiences, but here it is. And then I'll talk about streaming PCA, distributional convergence, and then our Bootstrap algorithm, consistency for that, and finally some simulations. Right, so the main question in Bootstrap is you have data, it's NIID data points. You can go beyond IID, but let's just say that for now, I'm just going to talk about independent and identically distributed data points. So I have a data set of size n. I have some estimator, which is estimating some sort of an underlying parameter of the distribution, the unknown distribution. And how do I estimate its variability? How do I know sort of, can I give a confidence interval, for example? Or can I say the variance? You know, you have, let's say you want to estimate the median, and you are basically just doing the sample median and you're giving me a number, that's a point estimate. I want to give some notion of variability around it. And this was proposed by Brad Efron in the late 1970s. So for a lot of statistics, typically what was done up until then is you will prove some sort of a limiting normal distribution, and a classical approach will be, oh, just go and work out, plug in things, work out the variance of that normal approximation by hand. Okay? And I can just estimate, just plug things in and estimate what the variance is. So great, so I'm done, right? The issue with this is, number one, these parameters will often need the knowledge of the underlying distribution. For example, you know, if I do the sample mean, we know that the variance involves like the sigma square, or the variance of the limiting normal has a sigma square in it. But you can estimate it just by looking at the sample variance. But when you think about the median, the limiting normal has something about the underlying density. So you need to do a density estimation or something like that. And also, needless to say, establishing the distributional convergence involves a lot of analysis. So the idea of Bootstrap is you perturb your data set repeatedly to mimic the sampling distribution. Okay? You pretend as if you are drawing many samples from the underlying distribution, but really you are just doing that from the one data set that you are given. And the way I think about it, it's kind of like replace the weight of a ton of complicated calculations by computing power. Just plug into your computer, let it do the simulations. lot of cases, there are some cases where it won't work, but in a lot of cases, you will get an estimate of the variability. Oh, and needless to say, please stop me whenever you want. Okay, so here is a Efron's classical bootstrap procedure. I give you a data set. You are generating B replicates by sampling with replacement from that data set. Okay, so you are, and from each one of those data sets, you are estimating your whatever parameter you are interested in. Could be mean, could be median, could be the beta vector, the weight vector in linear regression. And once you have all of these, you kind of treat them almost like, oh, I basically generated lots of data sets from the underlying distribution, calculated my estimate on each one of them, and then I can get a histogram. And of course, this is a very simplified picture. Many other ways of perturbing the data. You can do Poisson sampling, you can do multiplier bootstrap. That's kind of what we will look at today. Let me move on. So when I talk about bootstrap consistency, what do I mean? What I mean is here on the left, you have the true CDF of your estimator, right? So you have a theta hat. And here what you have is the bootstrap CDF. So you are basically saying, when you are doing the bootstrap CDF, you are conditioning on the data. You are saying my data is fixed. So the randomness is coming from all the resampling. So it's almost like you treat your data as the population. So anyway, so this is kind of like the bootstrap CDF conditioned on the data. And what you are saying is you are looking at the kind of a Kono curve distance between the two CDFs, and you are asking this random quantity, is this going to 0? That's what bootstrap consistency typically means. So in our case, our theta n hat is going to be some sort of an estimate of error for streaming PCA. Okay, so that's kind of where we are going to plug things in. Something to always remember that it doesn't always work. You need certain smoothness conditions to be satisfied. We are not going to get into that. In our case, things will go through. Okay, all right. The one thing that I do want to point out here is classical theory for bootstrap typically assumes fixed dimension for like your parameter. I have a t there. Just think of that as that should be x1 to xn. Sorry. So the question is, can you actually get consistency for functionals in very high dimensions? And so the setup again is you have n data points, which are independent vectors in RD. And what kind of statistics can I look at, which will, for D very, very large, much, much larger than N, where you still have bootstrap consistency. Now, here there has been a lot of recent work. One of the things that kind of broke like a long-standing barrier is the paper by Chernozhukov et al. And then kind of want to should have probably had their name in red or bold or something, because they kind of changed, I think, a lot of the analysis where made it a lot sharper. Okay? And that has kind of led to a lot of activity in that direction. And of course, there are other things like, well, you give me a sample mean, I want to look at the L infinity norm, which is Chernozhukov et al.'s work and also Lopez et al.'s work. There is LP norm of the sample mean and so on and so forth. I just want to look at the Euclidean norm of my mean. What does that look like? Or other LP means for p bigger than 1. So there has been a lot of activity in these directions. Whoops, sorry. This is that red should have been only on the second one, because that's where we are going on now, streaming PCA. Okay. Right. So now let's.
By the way, what's the name of the Chernozhukov paper?
It's in the citations. Can I just show it to you at the end?
Oh, sure. I was just curious. Like, is it about does it have bootstrap in the title, or is it?
Yeah, it has.
Or was some other topic that happened to imply it or something?
I'll remember,
sure.
And I'll tell you at the very end. I don't remember it on top.
Sure, no problem.
It's basically under all the citations at the end of the very first few, I think. So we'll look at that. Okay, so here is my setup. I have n data points. IID means 0. You can go from mean zero to something else, some mean, but we are not doing that. D-dimensional space, covariance matrix sigma. And, so this is like the PCA problem we have all looked at many times. You calculate sample covariance matrix and you are interested in the top eigenvector. Okay, it's one of those problems which is non-convex, but the surface is kind of nicely well behaved. So the solutions of these are and their behavior is very well understood. So as it turns out, we can write that error also as this. This comes out of, you can do it, you can think about it multiple ways, maximizing the variance, like find me the unit vector, such that if I look at the sample variance, if I project the data points on that unit vector, and I want to maximize the variance, that's essentially just the sample variance of those points. So that's one way of looking at it. And if you look at that and you say that, well, you know what, I'm just going to do an SGD. Okay, so I'll look at my tiered data point, I'll take a derivative, and I'll just move along that derivative. It's a maximization problem with a certain, whatever, like the eta t, the step size. Okay? You can do that, right? And then, of course, there is going to be a projection because you are going to project it back onto the unit sphere because it's an eigenvector. We are looking at uniform vectors here. How do you do initialization? Just pick a unit vector uniformly on the d-dimensional sphere. And the way to do that is just generate a d-dimensional normal zero identity vector and normalize it. Okay. And turns out that this algorithm was actually introduced by Eric Ojaz in 1982. He was, and I kind of didn't know the history. Rachel kind of told me about this very nice history about Ojaz algorithm. And apparently he was inspired by the Hebbian principle, which was proposed by Donald Hebb, a Canadian psychologist. And I basically picked out that sentence right out of Wikipedia because I couldn't rephrase it as well as it is. It's like, the increase in synaptic efficacy arises from the presynaptic cells, repeated and persistent simulation of a postsynaptic cell. And all I take out of that is it's a very simple linear neural network, one node. Okay? The data is coming in, you are looking at a linear combination of that. That's it. So let's talk about what people have done about Ojaz algorithm. What is known? A lot is known, and there are sharp error bounds. So there is a little bit of notation here. Sigma is your unknown covariance matrix, and V1 is the principal eigenvector of that. Lambda 1 and lambda 2, I'm going to assume, are the top two eigenvalues of the covariance matrix. The way we measure the error of Ojaz algorithm is by the sine squared error. Okay, so you look at the Ojaz vector, you take the projection on the principal eigenvector, like the true principal eigenvector. This is what you want it to converge to. And then you look at 1 minus square of that because, eigenvectors are, flip a sign, still an eigenvector. Okay. This is the sine squared distance. And there has been a lot of very nice work. In particular, I'll mention Jane et al.'s work, and they get a very sharp rate, which basically matches the error of offline calculation of the principal eigenvector. So if I just, got all the data, did my sample covariance matrix, calculated my principal eigenvector, how well does that converge to the principal component, the principal eigenvector of the true sigma? And their result looks something like this. Let me just explain in words. So eta t is 1 over t, roughly, some constant over t. There is this lambda 1 minus lambda 2 that has to come into play. Then with a constant probability bigger than half, the sine squared error is going to go down as 1 over n. Okay. And this giant, I don't know what that is. It's like a giant nu or something. And that's a constant which basically depends on the distribution of the data, or parameters of that distribution. And it is an absolute constant. Those are, that's kind of the assumptions they put in so that ends up being a constant. Okay, so this is known. So what I want to talk about is, can I establish a distributional convergence for, can we establish a distributional convergence for the sine squared error? So one of the things I want to clear up from the very beginning is that I'm going to use a constant learning rate. My learning rate, the eta t, I'm just going to fix it at something like eta n over n. This eta n is something that's growing very slowly with n. Now, if you look at Ojaz algorithm with some initial vector u0, the final thing ends up being something very complicated like this. Okay, so what's happening here in the numerator, what you have is a bunch of matrix products. Okay, so you have looking at identity plus eta over n, and this is because the eta is a constant outer product of xi transpose, and the product of that entire series of random variables, d-dimensional random variables you got, multiplied by u0 divided by the norm. This is not hard to see, just write it out and it just pops out to be like this. One of the questions is, why will something like this work? And there is some very nice work by Rachel and her collaborators actually, which talks about kind of the, like product of random matrices and how well they concentrate around their expectation. So if I just do a very hand-wavy sort of explanation, just look at the numerator and say that, hey, let's look at an expectation of that. On an average, what's happening there? What happens is, because it's a product of independent things, the expectation just goes into each part, right? And what you will have, an expectation of xi transpose is sigma. So what you will see is some sort of a matrix exponent like this, times u0. And essentially the matrix exponential is just blowing up the eigenvalues if you think about it, right? So it's basically taking all the eigenvalues of the original matrix and then just exponentiating them. So if your eta n was log n, for example, then we basically have something like n to the power. Like you will really blow up the magnitude and the gap between the first eigenvalue and the second eigenvalue. And we all know when we do power iterations, that gap is what matters. So this is what Ojaz algorithm is doing. It's kind of like separating things out. Right. Are there questions at this point? If not, that's great too. I'll just keep going.
One quick question is, this is sort of a stupid question, but since why isn't there like a logarithmic dependence for power method on the gap, the eigengap there? And it seems like in your bound, it's quadratic or something.
So
in the convergence bound.
Here?
Yeah.
So typically, so why do you think there should be a logarithm? So you are saying that it's kind of, if you do a normal power method, then it will have something like lambda 1 by lambda 2 to the power.
Yeah.
This is behaving slightly different from a normal power. So now normal power method, you apply the same matrix again and again.
Oh, right. I see. You're doing like a gradient an iterative update step.
Exactly.
Okay.
This is kind of like one data point at a time and what's happening on an average.
Okay, thanks. I get it.
Right. So I'm gonna just show you a really simple scalar case, and I think we'll just like go with that, and I'll skip some of the calculation. But I think this gives you a fairly nice idea of what's happening. So let's just do a scalar case where no xi transpose, just xi squared. Okay, and my eta n is 1. So I'm just gonna say that the numerator is a product of 1 plus xi squared by n, and divided by, that's essentially the denominator you have. It's basically just the expectation of that thing. Let's look at what that behaves like. So if you just write it out, like expand it around its expectation, it's going to have a really not nice looking expansion. But let's look at that expansion for a second. So the first term in that expansion is going to be, can you all see my mouse? Yes. Okay. So the first term is, So the first term is going to be something like an average, okay, average of IID things. And then you are going to have really complicated looking things in the remainder. The beauty of the remainder is all of those sums, they're all uncorrelated. even though it's not clear when I write it out like this, if you just took like the quadratic term and wrote it out, you will see that they're all sums of uncorrelated random variables. So it's very easy to control that remainder. Okay? And overall, the first term dominates and the first term behaves like a normal. So this is kind of where there is some hope of a normal convergence of something coming in. Okay. So not sure if you know about what like use statistics in like theoretical stats. So it's kind of a wide class of statistics, and the way you analyze them is by doing this Hofding decomposition. Okay? And the idea there is you are giving me a very complex looking statistic of n IID data points. I'm going to take that statistic and I'm going to project it down to different spaces. Okay, and these different spaces are going to be orthogonal to each other. And these projections are kind of, think of this as approximations of that complicated looking statistic, which is not necessarily a sum. Okay, because if I have a sum, then I can tweak out a normal distribution somehow. So anyways, the first term ends up being projection on the linear space of random variables. So it looks like a sum of random variables, converges to a normal distribution. Second term is basically quadratic. So you are looking at functions of pairs of random variables. Third term is going to be like 3 of them, 4 of them, and so on. So these terms are all sums of uncorrelated random variables, and they are also uncorrelated with each other. So that the spaces you are projecting to, they are in some sense orthogonal to each other, which is why there is this like huge literature on analysis of statistics. So, okay, let's keep going and let's ask ourselves, fine, so I now have a matrix, what about the matrix? Turns out the same sort, even if it's not a use statistic really, Hofding decompositions are very general, and you can do a similar Hofding decomposition here. First term is the expectation. This is what we talked about, right? You know, like just do an expectation, and Bn is the matrix product that I showed you. Second, so that's going to look like this, that the blue matrix is just a constant matrix, and I just multiplied n times. The height projection of the first term is going to look like something of this sort. So I have this formula, and doesn't look nice. So instead, what I have is also this picture. All that's doing is you have like n constant matrices multiplied together, and then you are inserting this mean zero matrix at 1, 2, 3, 4, the ith place, and so on. That's what that sum looks like. So in some sense, it's kind of like an average of independent mean zero matrices. If you look at the second term, you are going to essentially have the same sequence, but now you are plugging in pairs of matrices. So like, you know, the ith place has xi transpose minus sigma, jth place has xj xi transpose minus sigma, and so on. And again, uncorrelated. That's kind of the key here. That's why you can do something about this. And right, so this is like on eta squared times average of uncorrelated mean zero matrices, so on and so on and so on. Okay? So if I look at, so let's go into the sine squared error. And if I look at the sine squared error, then it can be written, expressed as this. And this is not something we did. This is kind of well known. So what you are saying is, you know, the denominator has the norm of the full thing squared. The numerator has some sort of projection or the orthogonal subspace. So V-parp, I'm not sure if I talked about V-parp already. If I didn't, I'm sorry. It's basically a matrix where you are just plugging in all the orthogonal vectors to V1. So it's like the orthogonal subspace of the principal eigenvector of sigma. So this is what Ojaz, the sine squared error ends up looking like. Right, so what we are going to do is we are going to look at that numerator, that vector. This is like a long vector in pretty high dimensions. And what we are going to do is we are going to break it up. Okay, we will, whoops, that's right. So V-parp is this matrix, and I should have had it in the slide before. So very simple decomposition. You say that, well, you know what, U0, let's break it up into projection along the principal eigenvector and all the orthogonal ones. And then you will show that this whole orthogonal bit is very small, so it goes away. So let's just focus on the first one then. And if you look at the first one, and again, just write out this ordering decomposition I showed you, what you will have is the first term. This T0 is, it's basically, T0 is the constant, some I plus sigma to the power n. So if you multiply by these orthogonal matrices on both sides, just disappears, goes away. Good, so it's gone. The first term is what we will focus on. And all of these terms, all I want to say really, don't want to spend too much time. All I want to say is that they're very small. And let's just move on. And that just pops out of the structure of the Hopton decomposition. So let's look at this, the second, the height projection. What happens there is exactly what I showed you before. You have sum over I, some stuff, and then xi transpose minus sigma times a vector. The stuff and the vector, by the way, I should have had an I for them because they're changing from one I to another. But essentially what you have is sum of mean zero random vectors. So essentially your hope is that this should behave like a normal after suitable scaling. And that's where our distributional convergence is coming in. So if you remember, and if you don't, here it is, you can just go back all the way. So we were, the sine squared error has the norm square of that vector that I just showed you. The vector behaves sort of like a normal distribution. So a square of a normal vector should have sort of like a, like a quadratic form, like chi-square. So that's kind of what you expect from the limiting distribution of Ojaz, the limiting distribution of the sine squared error that you get from Ojaz algorithm. Right. Yep. So this is essentially the theorem. Okay. Right. So
Purna, how do you deal with the fact that they're not IID, they're just independent and mean zero?
So that's a great question. So there was already a paper which deals with sums of IID random or averages of mean zero IID random. They are mean zero, by the way. They are all mean zero because the stuff and the vector are constant. That makes sense. So
yeah, but they're not IID.
They're not IID, but they are mean zero.
Okay. Oh, I see. And you're saying that's enough.
That's enough. Yes. I mean, if you need to kind of put some conditions in, of course, and I'll talk about them in a second. But if you basically show that not one of them just takes over and there is some uniformity over there.
Oh, okay. Okay. So you do need an assumption like that. Okay.
We are definitely going to need an assumption like that.
Okay. Gotcha.
And so this is the hidden under this whole regularity conditions on moments. And these conditions, as I'll show, they're not very far from the conditions that are typically used in the analysis of Ojaz algorithm. So the thing to note here is this eta it has a large range. Like you can go all the way up to 10 to the power 1/3. And if you, under all of those conditions, what you can show is this is kind of the bootstrap consistency that I showed you. You are basically showing that asymptotically matches the distribution of a chi-square. And this Zn, it has, and let me talk about it in a second. So what does that theorem mean? A bunch of things that are takeaways. Dimensionality can grow very fast. You can do like e to the power n to the power 1/3. Holds for a large range of eta. So traditional approaches basically assume that if I look at xi transpose minus sigma, not traditional approaches, I should say, like most of the literature assumes that this xi transpose minus sigma, the operator norm of that is bounded almost surely. That's where you can actually do anything in even high dimensional PCA. And all that's saying is, right, so what we need kind of the expectation of that thing squared has to grow slowly. And why will that ever be satisfied? What kind of data sets? So it is satisfied when you say there is a variance decay of the, like if you look at the marginal variances of the coordinates of xi, there is a decay there, which is, it has to be a strong decay. And all that's saying is there is a low dimensional problem hiding in your super high dimensional data set. Okay? There is some low dimensional structure. So that kind of a variance decay condition pops out in other results on high dimensional Bootstrap, high dimensional PC, and so on and so forth.
So if they're sub-Gaussian, then you're in good shape?
Yes, yes, sub-Gaussian with a variance decay. The variance decay. So I can't have, for example, like all the variances are of the same order. That's going to get us killed because then there is action everywhere. But if you have sub-Gaussian with variance decay, it should be fine. In fact, that's one of our examples, sub-Gaussian.
Okay.
And when you say that kills you, does that kill the analysis or also the Bootstrap algorithm?
Yeah, see, the Bootstrap algorithm will work only when there is this limiting normal distribution. So typically, for almost all Bootstrap, there has to be a limiting normal of some form. That's like my rule of thumb for Bootstrap to work. The moment the limiting distribution ends up being something other than a normal, Bootstrap tends to fail. Like, this maximum of uniform random variables is a classic example of that. But if it fails here, the Bootstrap algorithm won't work either. So they are
saying it won't be limiting normal if all my lower eigenvalues are.
Yes, it won't be. I don't know what it would be. And I can show you some plots if I have time, which basically shows that, the moment I throw out the limiting, the variance decay, things are kind of not quite working as planned. Okay. And of course, what we also tried was, we took our convergence result and we said that, let's just turn it into error bound and see if it matches kind of what is known. And it does match the rates up to logarithmic factors, though. Okay, log of n. So finally, let's talk about Bootstrap. And I'm running out of time. So, but please, stop me because all I really
you have plenty of time. Plenty of time.
Okay. Okay. Good. I wasted so much time in the beginning, just figuring out. Anyways. Okay. So. Online Bootstrap, let's talk about that. And again, what I'll do is I won't bore you with the gory details, but I'll give you some intuition and the final kind of result. Okay, why should it work? So one thing that we could say is, well, you have a limiting distribution. It's some form of a chi-square. You know what the covariance of those Gaussian vectors are. There is a closed form. Why don't you just go in and plug things in and estimate that? Right? That would be one way of doing it. I don't really need to do Bootstrap. Trouble is, all those parameters are going to need the knowledge of my sigma. So I'll have to estimate the covariance matrix. And the beauty of Ojaz algorithm is that I don't have to estimate the sigma ever. I mean, I never really sit down and build my covariance matrix. It just happens in this nice fashion of online algorithm, just by seeing one data point at a time. Right, so that's why we are going to do Bootstrap. Okay, again, let's go back to the scalar case. So here is a natural algorithm to do a Bootstrap, and let me kind of explain what I mean by that. So before I didn't have the ZTI there. All I had is 1 plus 1 over n x squared. And I'm basically replacing all my xt transpose by xt squared. That's it. Okay? Because it's a scalar, it is very simple. Now what you will say is at any time in that algorithm for every update, and this is, you are going to maintain a series of perturbed version of that update. And you will do that by, this is one way of doing it, this could be one way of doing it, just multiply each one of those data points by a normal random variable, normal 1, 1. So, on an average, the mean is, it seems like the mean should behave correctly. We are going to look at the variance in a second, but this is kind of the idea. And again, it's nothing new. Online Bootstrap has been used with SGD and other update methods. So, but it hasn't been used with Ojaz algorithm per se. So if I use a multiplier Bootstrap like this, let's look at what does that behave like. So, and I'm gonna again be hand wavy and say that, well, let's look at the Hayek projection. and if you remember what the Hayek projection does, it takes this very complicated looking product, projects it down on the linear space of random variables. It basically looks like sums. In this case, it ends up being IIT. So if you do look at the Hayek projection, and now the Hayek projection is going to be conditioned on the data, because in Bootstrap world, data is fixed, and the z's, the normal multipliers, those are random. So everything, I don't know if you remember when we talked about Bootstrap consistency, we basically said condition on data, find me the CDF of the Bootstrap statistic. Okay, so if I condition on my data, this is what I get. Okay, and if you compare with the Hayek projection of the original thing, this is what it looks like. Okay? So this was like our very first few sites where there was no Bootstrap. I was just looking at the first dominating with the linear projection. So let's look at this for a second. So you know, like mean zero, the first order thing, like both has mean zero, because I took my ZT to be normal 1, 1. So that's good. But what happens to the variance? If you look at the variance, what you see after a little bit of calculation is, sorry, I'm just trying to move the window here. Right, so what you see is, so you know, it's an average of independent things. So calculating variance is very easy, and I'm missing a 1 over sigma square n here. I'm sorry about that, but that just goes away. Roughly, there is a term missing here, so it's not quite right. Okay, and it's off. The variance is slightly off. It's like off by this sigma to the power 4 sort of thing. So how do I fix it? Well, the way to fix it will be to do this sort of a thing. So where you are saying that I won't just do 1 plus z times x squared. I will take the mean out first, and then with that centered random variable, I'll throw in a multiplier, which is normal 0, 1 now. Now, if you forget about all of those formulas, just believe that it works. The trouble is when I take it to the matrix form, it boils down to the sigma square is becoming sigma, and this xt transpose is this. And then you are like, I don't know my sigma, so how am I going to do this? Right? That's the whole point. So I can't really do a bootstrap, it seems like, in a consistent manner if I don't have a knowledge of my sigma. So chicken and egg. So what we did was like a very simple fix. We said that, well, you know what, this sigma thing, it's pretty well estimated by this xt. Well, not well estimated, but on an average has the same expectation as xt transpose. Let's plug that in. And instead of looking at xt transpose minus sigma, because I don't know my sigma, plug in the xt minus 1 transpose. It's kind of like a difference of the 2 outer product matrices from one step to another. And the moment you do that, the variance blows up by 2. So this is why there is an additional scalar. So that's not really something to worry about. The point is, if you do it this way, everything works out. You have a bootstrap algorithm with the right variance. So here is the final bootstrap algorithm. So you are going to draw some U0 uniformly from the d-dimensional unit sphere, fix it there. And now you are basically going over every data point. So the first step is where you are maintaining your Ojaz vector. Okay, this is kind of like without bootstrap. And in the second one, you are maintaining a set of B bootstrap vectors. Okay, and finally, and then of course there is a normalization. You can't just multiply, you have to normalize always. And at the very end, what you can do is, how do I do sine squared error? Look, the main problem with sine squared error is it has a V1 in it, right? It's 1 minus V1 transpose Ojaz squared. I don't know my V1. So what you do is you pretend you do plugging, which is like, again, like the very famous principle in statistics. It's not, it's so natural, it's not even a principle, right? You don't know V1, so you plug in by the parameter estimated on the whole data, which is the Ojaz vector. So instead of V1, I plug in my UN, which is the Ojaz thing. It's coming from the very first step here. And this UNI are basically these bootstrapped vectors. So that immediately gives you a histogram over sort of, like the sine squared error of all these replicates of the bootstrap. Let me stop for 1 minute because I packed in a lot and see if you have any questions. Okay, I'll keep going. So all we have done so far is very simple online bootstrap algorithm where there is added computation. You are having to maintain like a size B set of vectors, but B just has to go to infinity with N. So if you're, for all I mean by that, if you're a large N, pick a larger B, but doesn't have to go as D or N or anything like that. Okay. All right, so this is bootstrap consistency, and again, looks sort of not nice, but the idea is very simple. All my assumptions from the previous theorem has to go through, and here there is a lot going on. All that's saying is I need the norms to behave well. So the kind of like, this probability that this should be a 1, probability that the largest norm is growing too quickly with N, that's going to 0. And again, that gets satisfied under appropriate variance decay, similar to the first theorem. And this line, all it's saying is exactly what we had before. The only thing is there is a P star. P star basically means conditioned on data. So you are looking at your bootstrapped, the conditional distribution of your bootstrapped sine square errors. And you are basically saying, well, if I look at those two CDFs, this is the truth. This is kind of what you will do if you just generated lots of data sets, knew your V1, and then calculated a histogram from that, calculated a CDF from that. Okay, so we are basically showing that this goes to 0. Right, okay. So simulations. So let me do something. Let me kind of answer Eric's question really quickly. So here is, all we did here was we generated data from a uniform distribution and then just multiplied by a covariance matrix to get them all kind of dependent on each other. And we force the variance decay by this very simple operation. All this is doing is, depending on beta, you are going to have different rates of decay. So if beta is very small, it's very flat. Beta is 1, you're getting a pretty strong variance decay. And then, we did, this is really just proof of concept, right? So you fix your initial U0, you draw 500 data sets, run streaming PCA on each one of them, and then construct an empirical CDF of the truth. So this is how you estimate your truth. And then, of course, you do the same thing with Bootstrap. So there, you fix your data, and you are just doing about these 500. So you are maintaining 500 Bootstrap replicates. And finally, you are again calculating the Bootstrap CDF, okay? Where the inner product is, you're doing the inner product with the Ojaz vector, not the V1, because I don't know my V1. And so here is kind of the two pictures. And this, again, this is left panel, this is right panel. I thought I fixed it, but apparently not. So the difference between the two is kind of the imbalance of N and D. So the first case, N and D are very close. Second case, N is much larger than D. And always N is much larger than D. It works out nicer because it's almost like, I have more data points than the number of dimensions, and things start behaving more like classical sort of statistic, more classical things. So what you can see is, and N is just, for the left one, just 1,000, okay? The red is the true sampling CDF, the blue is the bootstrap CDF, and they are close, although in the beginning there are, even they look very close, there are gaps. That gap is going to get smaller and smaller if I increase my N. And you can see that if I just fix my D, increase my N, and that gap nearly sort of goes away. And here is, and again, this should be right panel, sorry. Here is where beta is 0.2. Okay, so there is very little variance decay. And what you are seeing is, and also look at these numbers. So what I'm plotting is a CDF, right? And I have scaled appropriately. So this should behave like a random order one random variable, P1. So before I had kind of numbers, they don't have to be all between like, these numbers where I don't know why they're between 0, 1, but the point is they were not blowing up to be 100 and a 50 and so on. That's happening here. So it's not really converging. So not that immediately tells me that when I scale, it's just blowing up. Something is not right. And well, it kind of seems like they are similar for the large and small d, but again, the numbers are all blown up. So the convergence is not really working. So the approximation is not great, right? So the one thing that I do want to point out here is this. So I kind of made these plots yesterday. So let's say that I do the same uniform distribution thing with this covariance matrix. Okay, so there's a lot of action happening on the top 100, and then nothing is happening in the rest. So it's like, identity matrix. What do we expect? And somehow the whole point of this is to say that if I give you bootstrapped CIs, and if I calculated the true sine squared error, are those CIs going to contain my true sine squared error? And that's what I'll show you. So this is, for this particular example, if you use this eta, which is again fixed, so it's like 0.1 times log n over n, works really well. And what I'm showing you is kind of like the bootstrap CIs, the CIs obtained from the bootstrap replicates. That's the blue, like the up and down, over time. So as I keep seeing more and more data points, and it's like the last, like 2,000 data points of my 3,000 long data set. And you can sort of see that it's a 95 percentile, 95% confidence interval, right? So, and you can see that like the red line is typically falling within the two blue lines. And that's kind of what we had hoped. And you see that the numbers are pretty small, and seems like, if you wanted to do a stopping rule and said that, I'm gonna stop when based on these bootstrap replicates. Again, I have no theory for this, but that could be plausible. And here is a eta that doesn't work, because what happens is the Ojaz vector keeps back and forth, oscillates a lot. And you can again see that here, we are again plotting the 95 percentile interval of the sine squared error. And you can see that the red is the true error. It's about 0.6. And it's always kind of in between this 95 percentile bootstrap error. And it's basically telling you, it's giving you some notion that it's not working out, things are not converging. That's it, really. Yep. Thank you. Oh, I finished.
Thanks. Thank you, Purna. We've got a few minutes for questions.
So I have one question.
Yeah.
So you have this assumption on the eigenvalue decay. Can you tell if those are satisfied? Is the way that you could tell, oh, I know that my estimate may not be good, but I know that it's not good.
So you are asking, how do I know that my data is actually, how do I know that the variance decay is satisfied?
Yeah, or like, can I certify it? Yeah.
So I feel like you should be able to certify it if you were kind of using the first part of the data to just calculate marginal variances. So you can't, how do I say this? So I think the conditions are possible to check. So if you give me a little bit of data that I can throw away, and I'll just keep looking at the data to have estimates of my marginal variances for all I is equal to 1 to d, I can just look at that, like the histogram of those variances. And if it's decaying fast enough, then the original thing should be satisfied. But
don't you need to know the direction to estimate them? I mean, it's in an arbitrary basis, right?
Sorry, what do you mean, the direction?
Like you care about the marginal in the basis of the eigenvector.
So this.
I don't know though.
No. So I'm not talking about. Right. Sorry. So what I'm saying is the marginal variances of the random variables themselves without any eigenvector, without any projection. So if the data is coming so that kind of, if I look at the variances of if I look at the diagonals of the sigma, for example, there is some decay there, then it should work. And I'm saying that it's possible, I think, it's a great question, I haven't thought about it at all, but it's possible to do that if you give me a little bit of data to figure that out. So you keep giving me data sets, I'm just thinking, and I keep maintaining sort of, like keep a running average of, not average, but like you keep calculating, estimating the variance of the different directions. Like you give me d-dimensional vectors, right? And I keep calculating variance for each.
Wait, so then your assumption is not basis independent? Because isn't Ojaz's algorithm basis independent? Shouldn't it?
So when you say it's basis independent, you mean?
If I like rotate every vector by the same rotation matrix.
If I rotate every vector by the same rotation matrix, yeah, the PCA directions, XX transpose should be the same. Right, but I mean, it's the same. If you are giving me a data set and you are basically saying that they're all rotated a little bit, right?
Rotate a lot.
Or a lot, it doesn't matter. So I should still be able to calculate marginal variances, right?
But I guess like, I don't expect my individual coordinates to have decaying variances then. Because maybe the top eigenvector is in the all ones direction. And that direction is just much bigger than all the other eigenvectors.
So let me think. So
I'm confused about something. Can I ask a question?
yeah.
So these assumptions are weaker than the Jane assumptions.
Right, they are.
And the Jane assumptions are basis, rotation, and variant. Right?
Yes.
So I would think that these weaker assumptions also are.
Yeah, these are rotation invariant as well, because if you just do xi as xi times the rotation matrix, on an average, the sigma should be the same, right? So what I'm trying to, I think, answer is how will you sort of check whether, like, if you are given some data, how will you check whether the variance decay is satisfied? And my first answer to Eric was just estimate the variances. And I think he thinks that, and I need to think about this a bit, that if you kind of rotate things, then why will like marginal variances, why will they give you variance decay? Yeah, I don't have a good answer for that.
Okay, so just to be clear, your actual condition is on the variances in the eigenvector directions.
No, it's a condition on the sigma, like the covariance matrix.
Mm-hmm.
And if you look at how we built the covariance matrix with the variance decay, we basically took a covariance matrix that doesn't have variance decay and just left and right multiplied by like a diagonal that is going down very quickly. So that's forcing the variances of the, like, it's basically saying in the D features that you have, there are a few which are very active, but the rest are kind of really trailing. There is not a lot of action going on there. So that's what the conditions are.
I mean, if you don't have this condition, I don't think you really have a right to be doing PCA, because it's basically a condition that says you have some approximation of your covariance matrix by a rank 1, by the rank 1 xi transpose, right?
Right, but you could have eigenvalue decay just in terms of the principal components, and that would make sense to do PCA.
It
That's
would
what
make
Eric-
sense.
If the covariance matrix is just 1 in every single coordinate, that's rank 1, but it's diagonal doesn't decay.
Oh, 1 in every coordinate?
Yeah, diagonal and off diagonal. Just like all your coordinates.
Oh, okay. So I think I'm beginning to understand. So yes, so I think that's a great example. So you are saying if I give you the all ones matrix, then the eigenvalues, it's that rotation. The eigenvalues is n 0 0 0. So clear, very clear that you have decay. But if I look at just the diagonals of it, right. No, that's good. So if you are asking me, how do I measure, like if I have a test for when the variance decay is satisfied, then what I just said doesn't work about the marginal variances. You are quite right. What else could you do for just to check whether it is satisfied? Oh, the other thing that you could do is sorry, I'm thinking. And I don't have a clearly very good answer for this, but it would be to basically just look at the norms of those vectors as they are coming. And the trouble with this is, you don't have a growing D situation. If you had, I'll say that, check for different dimensionality, how the norm is growing. And if the norm is growing very quickly, then you can't really do anything there. So yeah, I don't have a very good answer for that, how to test for exactly that condition being satisfied. Yeah. And you are right, I think just marginal variances won't exactly work because you will need the eigenvalues. The eigenvalues will basically give you the decay. Yeah.
All right. Since we're going to meet outside for anyone who's interested, let's all thank Purna for a very interesting talk. Thank you, Purna. So we'll see you either outside or at the next talk.
Okay.
Thanks, everyone. Bye-bye.